Welcome everyone to this new session of the Gamma seminar. Our speaker today, Javier de Lucas, will give us a super talk on supergeometry. This will be the first part, as he mentioned. So whenever you want, Javi, the stage is yours.
Well, thank you, the organizer, for the invitation.
You're very welcome.
I hope I will get a certificate. Okay. Welcome everyone. Thank you for letting me, for hearing me once again. And today I will give a very basic talk about supergeometry. Well, the basic is about that it is the fundamentals about supergeometry, for linear supergeometry. I will not probably go into supermanifold. Okay, so let us say, to be sincere, is that one of my students gave a talk about it. So I took what he did and I will change it a little bit, but many of the things here are from here, yes, but by means of many additions and many commentaries. So once I have recognize all the work, let us say what I meant to give today. Truly speaking, here this is meant to be a 2 weeks talk. Okay, as I said at the beginning with Xavi, we decided I will do this week and next week. So for the first talk, let me focus on the linear part. Okay, superalgebra and the basics of sieves, and then on the second talk I will go for the non-linear thing, for the real differential geometry with supermanifold, differential calculus on supermanifolds, and a super-Poincare lemma. I think I will not do it. I will keep just my talk on the main things. Let me just tell you that supergeometry is an extension of standard geometry, for the case when the basic field in which we are working, it's not commutative, and it's not even a field, okay? So it's something what I will talk you in, roughly speaking, it will be a little bit like what you know from linear algebra, yeah, but there will be things that are not commutative, okay? With linear algebra, you have the multiplication by numbers, okay, functions and things of the sort. And in supergeometry, the main difference is that you will have things that don't commute among themselves. You know, numbers, the multiplication standard multiplication numbers, they commute, but in here you have another things. The roots of this theory can trace back to supergeometry, to super models and things of the sort, and to quantum mechanics, where they appear things that are fermionic and bosonic, and they naturally commute and decommute. So something of these things will be appear here. Okay, so once I have said more or less where this is coming from, yeah, let me start, but defining the main thing. So I will go through all these definitions. There are lots of them, but most of them, there are a copy of what you can find in linear algebra, just by adding a certain decomposition. Okay, so let us say that it seems that it will be a lot of definitions, but it's not that hard. Okay, I will try to explain it in such a way that it will be even easy to follow. That's the main point. So let us start by the first definition. And the first definition, as you can say, says that a vector superspace is a pair where B is just a vector space over a field. K can be the R of the C numbers, the complex of the is a linear endomorphism from B to B in such a way that alpha squared is equal to the identity on your linear space. So, as you can see, a vector space, superspace, is nothing but a superspace along with a certain endomorphism satisfying this condition. Okay, so let us describe what does this condition mean. Okay, because this is the main thing. What does it mean? So you have to take into account that when you have a 30 morphism like this, okay, like this alpha, okay. So naturally, you will have that alpha squared minus the identity on the vector space is equal to 0, and this means, okay, that you will have this decomposition. This is equal to 0. So for linear algebra, you know that this decomposition here means that your space B can be written as a decomposition into the kernel of this thing and the kernel of this thing. Yeah, this is something about linear algebra, and it's very easy. Yeah, everyone knows about it. It's something that one learns at the first the first year of your studies. So the thing is that you have two subspaces, this one, and you can see that this on this space alpha behaves like the identity. Yeah, on this space, and on this space, there is the kernel alpha plus the identity. Alpha behaves like minus the identity. Okay, so what you have is that your alpha defines a decomposition in such a way that on one space, alpha behaves like the identity, and on the second space, alpha behaves like the minus identity. And the other way around, I mean, if you have a 13 decomposition of B into two subspaces, you can define an alpha in such a way that it will be the identity on one, it will be the minus identity on the second, okay? And alpha square, it will be the identity, because on spaces here, alpha square will be the identity, and on the spaces in here, alpha square will be first the minus identity composed with minus identity will be the identity. So the alpha will be the identity on those. So it's an if and only if, okay? So what you have is that a vector subspace, as I said at the beginning, is that this is a pair where you have a 13 space and 13 endomorphisms whose square is the identity, but this amounts to the composing B into two subspaces B0, B1. Okay, so this is exactly a superspace. It's a vector space which is decomposed into the sum of two subspaces. Nothing else, nothing more. Okay. I can tell you that the elements of this power alpha will be the identity. They are called the even elements, and elements in here are called the odd elements. Okay. So once you have this, you have noticed that the vectors, every such subspace amounts to a sum of two subspaces B0, B1. You can define a certain structures. You can, for example, make a projection onto the even part. You can have a projection onto the odd part, and you have also injections. You can this thing inject into the total space, like for every B0, you can write B0, 0, or here for every B1 belonging to the space of odd vector spaces, you can give this one. Yeah, so you can have this way. So the other thing is that here you have a 13 decomposition of alpha, but this is a composition is trivial. As I said to you, the B, when you have a 13 super space structure in a vector space, you see that on a 13 subspace, the alpha behaves like the identity and the second like minus identity. So alpha can be written in this way. You know, you have a 13 pair of elements. Okay, well, I mean, you have a 13 element belonging to B. Since this is the sum of these two, this B can be written as a 13 decomposition of two elements, B0 belonging to this, B1 belonging to this in a unique way. So the thing is that the image of this element will be alpha acting on this and acting on this, but acting on this will be just this element, and alpha acting on this will be minus element. You can see that this is indeed the stake. When you have this B, you put into B0, you obtain this, and you do the injection. So you have B0, so it will be the same B0. And with this part on this B, will take up the pi 1 of this would be B1. The injection will give you the 0 B1, I mean the same one, yeah. And then with a minus. So alpha will act here like the minus. So this is the thing. So as you see, you can define equivalently a vector superspace as a triple B, B0, B1, where B, B0, B1 are k-vector spaces, and B is the sum of B0 and B1. Yeah. So example, for example, if you let me explain this, there are the typical example in supergeometry is an infinite dimensional vector space, and this can be the space of all differential forms on a manifold M. Yeah. So when you have this space, you can consider the direct sum of all forms with an even degree. So you can write this thing and belonging to C. Yeah. And you can see that this is B0, and then you can define the sum, the rigid sum of the odd elements of the differential form which have odd degree, and this is B1. So as you see, this space can be written as the direct sum of these two ones. Okay, so in this case, as I said to you, okay, the elements belonging to this space will be subspace will be called even differential forms, and those in here they are all differential forms. And if you follow this thing, you will see that you have a new definition of what I said, introduced before roughly, and the elements of B0 for a vector subspace, they are set to be, this is wrong, it's even, and the elements of B1 are set to be odd. Okay, now there is a certain type of element of a vector superspace that is very important, and these elements are the homogeneous elements. Well, homogeneous elements of a certain vector space, they are nothing but the elements that are or even or odd, and that's all. Okay, a vector element, a vector of a vector subspace is said to be homogeneous if it's or even or odd. Normally, the space of homogeneous elements of a vector subspace is written in this funny way. This is a symbol, and you see it's the sum, it's the union. Okay, union, because you cannot make the sum, because the linear combination, the standard linear combination of even and odd elements is not even or odd anymore. You can say because the even belong to B0, odd belong to B1. So if you sum just an odd and an even element, then normally will not belong nor to B1 or to B0. Okay. Now you can see that this thing, okay, it's just to say that there is a number 0 that is called the parity of the elements of B0. For every even element, we say that its parity is 0. For every odd element, we say that its parity is 1. Okay. And normally the parity is an element of C2. That means that we add the parities according to the Lie group structure on C2. That means that, for example, parity 1 plus parity 1 is not parity 2, it's parity 0. Okay, or parity 0 plus parity 1 is parity 1, and so on and so on and so on. Okay, one small thing, one remark is that the 0 belongs to B0 and belongs to B1. So 0 has parity 0 and has parity 1. I know it's a little bit weird, okay, So normally in works you will see in books that normally you don't pay attention to it. And sometimes the good thing is to say that zero has no parity, yes, to forget about, to avoid this kind of problems. But please, yes, treat zero as a particular case. I will not go into details because to deal with this in many occasions is a little bit tricky, cumbersome, makes things a little bit theorems and things like that a little bit worse. So let us say that zero is not even is odd and whatever. We will not focus on it. Okay, I don't want to go into details. I want to keep this simple. So far we have said that a super vector space is a vector space divided into two subspaces in direct sum. One of them is the subspace of even elements, the other one is the subspace of odd elements. We have said that the the union of these elements, even and odd, is called this subset, is called the subset of homogeneous elements. Okay, and now we go into the following part. In supergeometry, the standard one, like in linear algebra, is that we have to define what morphisms must be. Okay, so between vector spaces, in vector spaces are standard vector spaces. You can define linear morphisms. Okay, among all these linear subspaces, you can define a particular type of linear morphisms. And these are the so-called homogeneous morphisms. So the homogeneous morphisms between superspaces, there are 30 linear morphisms, which in a certain way, they preserve or they change the parity. So what do they do? What do they do is just that if you have a certain homogeneous element, okay, homogeneous morphisms, they are such that for every homogeneous morphism, you will have a number called the parity of the homogeneous morphism. And if you have a certain element that it is homogeneous, and this is the parity, okay, of this element, the morphism has a certain parity, and the image of this B, the parity, is given by the parity of the original number plus the parity of the morphism. Okay, this is the thing. So this looks a little bit weird, but it's very easy. Imagine that you have an F homogeneous, and this is very easy. Imagine that the parity of the morphism is 0. That means that the parity of the image of one element, homogeneous element, and its image is the same. That means that if you have an even element, okay, the image of it will be even. And you have a certain odd element, the image of it will be odd. Okay, so this is the first case. This is called, when the parity is 0, the morphism, the homogeneous morphism is called to be even. Okay, and the other case is when this is 1. In this case, the homomorphism is said to be odd. And in this case, if you have an even element, the parity of the image, according to this, would be 1 plus the parity of this. This is 0, so it will be 1. So what you have is that this belongs to 1. And if you have an element that it is odd, the image of it, the parity of this thing, according to this rule, will be 1 plus the parity of B1, means 1. 1 plus 1 in Z2 is 0. So this will belong to 0. So when you have homogeneous morphisms, they are linear morphisms such that when they are even, they map even elements into even elements, odd elements into odd elements. And when the morphism is odd, it maps even elements onto odd elements and odd elements into into even ones. So let us give an example. For instance, we go back to our space of differential form. We recall that it's the sum of two subspaces. That this is the sum of the even ones, yeah. I recall that this one, this thing. And this, I recall that is the sum to m plus 1, m belong to z. This, okay. So let us define certain things. For example, you have the differential operator. The exterior differential operator can be defined on exterior forms, yeah, and it is linear, yeah. You see that this is a superspace, vector superspace. Superspace. This is a vector superspace. So this is a linear morphism. And you have to take into account that when you have a certain omega, and omega it is even, the differential, it is odd. Yeah. So that means that for even elements, so for some of even of differential force degree even, the image will be odd. And if omega is odd, the image will be even. So you say that when you extend D to the whole space, if you have a certain sum of even differential forms, the image will be a sum of odd differential forms. So it maps even to odd and it maps odd to even. So this D, the parity of D is equal to 1 and it is at odd homogeneous morphism. Something of the sort happens with the contraction, yeah, but in terms of a vector field. This is a vector field, yeah. And this, you can see that when you have an even differential fold, the contraction with a vector field will be odd. When you have an odd differential fold, the contraction with a vector field will be even. So it turns that out that this is 1, is odd homogeneous, because it's linear also. And you have also the Lie derivative. And this Lie derivative, it does not change the order of the differential forms. You have a certain p differential form and it's even, the Lie derivative will be even, and it's odd. So it does not change the order. It maps even differential form into even differential form and odd differential form to odd differential form. So it will be, and this is an even morphism, homomorphism. Yeah, you can have also the double contraction with subvector fields that happens, for example, multisymplectic geometry, and you can see that this map is linear, okay, and it maps even to even, odd to odd. So this is an even homomorphism. Well, and you can do lots and lots and lots of things, okay. There you can also define the Hodge operator when you have a certain metric. This thing depends, okay, depends of the dimension of n, okay, and sometimes it's odd, sometimes it's even. There are lots of them. So the thing is that this thing looks like very abstract. It is very abstract, but all these things, all these notions, they appear in differential geometry, and it is fun because some rules that appear in differential geometry can be explained by means of all this stuff. So, well, the following thing is that when you have, for example, linear superspaces, normally you want to know how to produce new linear superspaces out of those you already know, yeah. So you can define the tensor product to vector superspaces. I mean, if you have a B and this is a vector superspace, you have your endomorphism whose square is the identity. You have W and you have the endomorphism whose square is the identity. So you can see that when you do the tensor product of vector superspaces, you can introduce again a structure of a vector superspace onto it by means of this morphism. Yeah, indeed, it's easy to see that when you indeed compose this with this twice, okay, it acts on the product of two elements. Remember, please, that this goes alpha, it acts on the first one. No, this will be, sorry. And this tensor product of morphisms is such that this acts on this and you have the tensor morphism. So it's something like this. Alpha times omega, yeah. And when you act this the second time on this, it will be this acting on this, it will be square, it will be the identity, this acting on it will be the identity. So it turns out very easily that this square is equal to the identity on this. So it works, okay? If you work out which are the root subspaces of this morphism, okay, the B0 and B1 for this tensor product, it can be proved that the elements that are 0 in the tensor product are the direct sum of the 0, 0 and the 1, 1. Okay, and those elements that are 1, that they are the odd part of the tensor product of vector superspaces, linear superspaces, is that the odd stereo even the direct sum, the even stereo with the odd. Okay, so this is the thing. This structure used to happen in quantum mechanics, because as I told you at the beginning, this has 30 relation with quantum mechanics, what is called bosons and fermions. So bosons, they can be understood in 30 models like differential forms, like odd, even differential forms, and fermions can be understood as odd differential forms. So by doing the tensor product of bosons and fermions, you can define new particles with new characterizations. Okay, when you have two fermions, you will be able to generate a boson, and when you have two bosons, it will be also a boson. But if you have a boson tensor product with a fermion, it will be a fermion. This structure, what I wanted to tell you is that this structure appears, for example, when you have quantum models. Okay, and it is used indeed. For example, if you let me tell you one example, when you have quarks, if I don't, I think that I can remember well, but I'm not sure, but let me tell you whatever. You have up, down, and charm, and think that it was something like, they are fermions again. So it happens that they can be understood as odd things, odd, and odd. It thinks that it was like this, up, down, and charm, maybe once up, second, because it was up, down, charm. No, I think that it was strange, maybe the third one. Maybe yes, up, down, strange. I think that it was like that. So the thing is that they can be assumed to be odd, and then what you can do, and it's fun, is to make the tensor product of these things. You can do an up, okay, and it goes here, okay, and you can do an up strange. It's like summing vectors, okay? You have this one vector, one vector, one vector. If you up, it will be two up vectors. You can be an up strange, okay? So it will be something like here. Here, no, so sorry. It will be up strange, it will be here. You can do an strange, it will be here. you can do a down stretch, it will be here, and you can do a down, it will be here, you can do a down, up, down, up. And you will have a nice diagram of this sort, okay? So this is a fermions. Somehow they are considered like odd elements. This is odd, odd, and odd. When you do the tensor product and you have two odd elements, this is assumed to be even. And you see, it's like the tensor product because you have this thing here, yeah? Tensor product of two odd can be considered as even. All these things you have in here, they are all of them considered as even. And the fun thing is that this diagram, it appears here, okay? It corresponds to certain particles. And more or less, this structure with superspaces can be used to describe all these particles. So anyhow, this is just an example and things like that. So let's go on. Okay, so we have talked
a
about...
comment.
Yep.
That this structure that was discussed about particles is called eightfold way, and it has its own Wikipedia page, etc.
Yeah. I mean, this structure is, but the thing I think that in Wikipedia is about the structure with these things. This is a representation theory. Indeed, the reason why quarks appear at the very beginning, it was because they were described like as representations of a Lie group called SU3. Okay, and they were found the fundamental representation. The fundamental representation, the free one is this, the up-down charge, and there is another one that is with antiparticles, that it is the covariant quadjoint representation, that is the induced dual, yes, things of the sort. And here you have things that they can be associated with this. You can do tensor products, you can do the tensor product of representation, things of the sort. And it turns out that all these diagrams, they correspond to real particles. And the fun thing was that at the beginning, when this was not known, there was a zoo of fundamental particles, and there was no structure on them. But this theory could explain the structure of these quarks. And it said that mathematically they can be understood like the invariant representation of SU3. And this is very well known. This is in Wikipedia, but I'm not sure that in Wikipedia they have the a super geometry interpretation of this. Okay, this is what I meant. This is the first thing. If you know, do you know it? Have you seen it?
This interpretation or these diagrams?
Diagrams for sure they're in Wikipedia, but the interpretation?
No.
That's the point. By the way, at the beginning, they thought that these quarks, they are just mathematical entities. They didn't think that they are quarks real. And this theory was nice because in one of these diagrams, there was a missing point. And the theory said that there is one of the representation where there is one place where there is no particle known. But by means of these diagrams, it was shown that there was a new particle and it was found. So this can be found in Wikipedia. There is a lot of theory about that, but the interpretation with the supergeometry, I don't think so. I think that it is on papers, but I don't remember exactly. Anyhow, thank you for the remark. And this is true. You can find these diagrams and the properties about this. And I will continue with superalgebra. Here we have described these superspaces, that I have said that this superspace is nothing but a superspace with a certain decomposition. We have defined morphisms of these superspaces, and there are linear, yes, morphisms. And these morphisms, the fun thing, the nice thing is that there are some very relevant ones. They are the even and the odd, the so-called homogeneous. And these homogeneous just satisfy that map even on to even elements, odd onto even in the even case, in even for the even morphism, and for the odd, they change the order. So the following element you have in linear algebra or in algebra in general is just the algebra concept. And algebra is just a certain space, okay, that it is normally is a vector space where a product is defined. This is just the most common algebra notion. There are lots of them, but let us focus on this. Vector space with a product. If you want to make a superalgebra, well, the only thing you have to do is just to make a decomposition of this space, of this vector space, into parts. And you have to tell how the multiplication has to work to deal with, to be compatible with the decomposition. So when you have an algebra that is an associative with a certain product, okay, and you have the composition because this is a vector space. And now the thing is that the product, which is naturally defined on the algebra, it has to satisfy that if you have two even elements, the product of them has to be even. You have even odd, it must be odd even must be odd, in the product of odd with odd, it must be even. So it means that the product is compatible with the parity, in the sense that if you pick up two elements that are homogeneous, they have a fixed parity, and you work out the product, the parity of the product must be the sum of the parities of the elements A and B. Okay, so the typical example of this is the one we had before, differential form, yeah? B0. Well, you know what is it? Even differential form, yeah? Even differential forms, and B1 all differential forms, yeah? And now if you have alpha belongs to the, or alpha, let's say theta, you have epsilon, and is well, let us say more general. You have things that belongs to this here, okay? This means that they are homogeneous. Okay. Now you have that this is an algebra because you have the stereo product. Algebra, yeah. So imagine that you have two odd elements, even elements, for example, even differential forms. If this is even and this is even, the wall is also even, yeah. If you have, for example, you have these ones that is at all 1, 1, to which space does this belong to? Odd or even? This is even differential form, even differential form. So the tensor product is, someone can tell me?
Even.
Even, yeah. If this, for example, if this is one differential form, is a phrase is an even differential form. And if you have this, odd or even?
Odd.
Yeah. And the other way around. If you have this one, for example, and you have this is all, yeah? So you see that you have the structure we said at the very beginning, yeah? That the product is compatible with the composition because the product of even elements is even, odd elements is even, and the mix even with all it all. So the parity is compatible with it. So as you see, this is just a stupid thing. Yeah, it's just a way of saying that the multiplication must be compatible with the substrate, with the composition differential forms. And the thing is that when you have a superalgebra, you know, it's an algebra that is a supervector space in such a way that the multiplication is compatible with the decomposition. Well, this superalgebra is called supercommutative if you, when you change the order of the elements, of the two homogeneous elements, the parity changes, and it changes in this way. Yeah. So you can see that when you have these two elements, yeah, this parity is just the order of this AB. Yeah, this is one way of telling it. So it turns out that this, if this is an even element, -1, even though it will be 0, it will be 1, it will be the same. So if this thing is even. So what you have is that this will be even too. And if this thing is odd and you change the elements, you will have an odd element. Yeah. So again, you can see that this works like with differential forms. Yeah. Because if you have a certain P differential form on M, and you have a Q differential form on M, you already knew that the exterior product of this, it will be -1. And now what you have to do, P plus Q, OQP, yeah? The change of the, wait, here there is something weird. Just a second, because this will be PQ. Yeah, because this is wrong. This is the multiplication, sorry for that. Now it's okay, yeah, now it's okay, sorry for that. Yeah, now it works. It wants me the multiplication. Yeah, so if you have, for example, like differential forms, indeed, this is the example. Yeah, if something goes wrong, you can go back to your example and you will see how it works. So what does it mean when you have this multiplication? It means that if one of these even, yeah, this will be 0, 0, whatever will be 0, and this will be, let's say, not this. So this expression means that even commute with everything. Okay, and if you have A and B and both of them are odd, they anti-commute, because the product of 1, 1 will be 1 and there will be a minus. So it turns out like with differential forms, yeah, when you have an even differential form, it commutes with everything, and you have an odd differential form, it anti-commutes with the same differential form. So a superalgebra is super commutative if the multiplications is given in this way. Okay, this is the thing. So let us go on, and now, as always, we have morphisms. We studied morphisms of super vector superspaces. Then we have superalgebras. We have to study the morphisms of superalgebras. So in superalgebras, the thing is that, as before, we have a morphism between algebras. Okay. Say that you respect the algebra structures as usually, but here we have to distinguish a special one. That this is a homogeneous homomorphism of superalgebras, and this homomorphism is such that when you have a certain multiplication of elements, okay, the thing is, when you pick up the multiplication of two elements and you make up, you work out the image of it, yeah, the image will be f of A times f of B, and there will be an extra term, okay? And this extra term depends on two things. It depends on the parity of the morphism, that again, it can be even or it can be odd, and the parity of the first element. Yeah. This looks sometimes a little bit weird. Okay, that depends only on the parity for the first thing, but one can check that this is indeed quite natural. Okay, then it can happen. Okay, it happens in many cases. So the thing is, what you have to remember, a morphism between superalgebras, okay, it's just a standard morphism between these superalgebras. I mean, it's a linear morphism because superalgebra is supervector space as a vector spaces. It's a morphism algebras, it must be compatible, but it's compatible in such a way there is a sign of difference. Okay, it will not be that FAB is exactly FA times FB. There is one symbol, one sign that it can be changed. Okay, so when you do this again, the normal thing about this is about thinking about differential forms. So, for example, you can think about a morphism. Imagine that you have a certain morphism between two manifolds. And then you have the space of differential forms on N, and you have the space of differential forms on N, and you have the pullback. Okay, so this is a superalgebra. Indeed, it's supercommutative. And this is a superalgebra. Yeah, they are super vector spaces with a certain decomposition between odd and even elements. And apart from that, you have a certain multiplications that it's compatible with the decomposition of each space. And this thing works because for every differential form here, you can make the pullback. Yeah. So this is this thing is a superspace. This thing is a superspace. This thing is linear. Yeah. Apart from being linear, it must be, well, it is homogeneous morphisms or vector subspaces, because if you have an even differential form, okay, on the space N, the pullback doesn't change the degree of differential form. If it was at the beginning even, it will be even. And if it was at the beginning odd, it will be odd. So this is included in the even part, and this is included in the odd part. So phi star is a even morphism. Sorry. Of superspaces. Now, when you have that this is an even morphism of superspaces, it means that the parity of phi star is equal to 0. So what you have indeed is that if you had two differential forms belonging to this, you already know from differential geometry that this is this. Okay, indeed, you can write the sign if you want to here. This parity of θ1, and this thing was said to be 0. Okay, is the phi star. So it is compatible. Yeah, the sign is a plus. So when you have such a thing, you can see that this is an even morphism of superalgebras. Yeah, the pullback. Indeed, you can go through all the operators you had differential geometry, and you can understand them in this way. Yeah. So okay, this is a morphism, things of the sort. Okay, so the thing is that there is one particular example thing, one thing that is very important in supergeometry, and this is the Grassmann algebra. A Grassmann algebra is a particular type of algebra. It can be shown that it is a superalgebra, okay? But it is an algebra of a particular kind because it has a certain basis, a certain set of generators we generate the whole thing. So here you have this thing, one definition, okay? I hate this definition, but it's the standard one. A Grassmann algebra K-L is a K algebra generated by the elements 1, beta 1, beta L, which satisfy the relations that 1 commutes with everything, and beta I, beta J anti-commute with themselves. So, and these things, you can work out the product of all these things, and you will get a vector space with a 30 multiplication and things like that. Okay, so take into account that here, when you have a Grassmann algebra, you have this element that can be multiplied by numbers, so it will be K, okay, within this KL algebra. Now, you have these generators. So this is a vector space because the Grassmann algebra is a vector space and generated by this. You have L. So you have the linear combination of these things. Okay? That are different from this. So you have this. And now you can start making multiplications of these elements. When you multiply one of these, that gives nothing. But then you can multiply all this stuff between themselves. But they are anti-commutative. So when you have 13 elements, they will generate then, apart from that, you will see that you can start making the products of all these things. And for example, you can multiply everyone with everyone. By this rule, it must be equal to the minus thing, so they must be equal to 0. So it turns out that the square of these elements is equal to 0. Okay, the product of these elements with themselves is equal to 0. But with different ones, they will give something new. But you have to take into account this anti-commutative. So every 2 elements, whatever they do, no matter what is the order, they generate the same thing. So at the very end, when you have these things, products, linear combination of products there will be different, okay? Will be all those that can be obtained by combinations with a repetition of these 2 elements. So these 2, they are the number of elements 2. This is the number of elements you will get. If you get 3, you can repeat the thing and you will get that you cannot repeat 2 elements because when you have 3, because if you repeat, then it will be equal to 0, and then you will have to get all that's L3, then you will have 4, and things of the sort. You will have L over L, that is equal to 1, yeah, and then you will have nothing, because when you will have L plus L elements of these, some of them, they can be repeated and they will be 0 when be repeated. So at the very end, the Grassmann algebra is a sum of this sort. Okay, you will see that summing of these things, the dimension of this is here, the dimension of this is this, blah, 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 blah. So you see the dimension of this sheet is just as 2 level 2L. Yeah. So, and again, what is the typical example? Well, the typical example is just differential forms, okay, but at a point. So imagine that you have a 13 points, the constant function, and you have 13 dxl, yeah. So these are 13 points, they are covectors, so all the elements you will have when you have this number are sorry. The vector space generated by this will be the cotangent to RL, and then you will have to get the tensor products of this sort. Obviously, this is equal to 0 when they are the same. When they are different, they are different. So you will get the so-called the anti-symmetry tensor product. Normally, that is called this thing. Then you have the 3 elements, they will have this thing and things, till the moment you will have this. Okay, and this is the Grassmann algebra. This is just called the Grassmann algebra. When you have this Grassmann algebra with this thing, you can divide the Grassmann algebra, picking up the elements we have odd powers, and to say that these things, they are the B0, and you can pick up the odd ones and to see that this is power. So the Grassmann algebra is a superspace. What you have aquí is nothing but notation about how to make these products. Okay, so this is what I said before. It's not even interesting because I have already said everything. Okay, and now I have the last structure, and I will finish because it's been an hour, and I will finish with super rings, and then I will left supermodules for other time. So super rings, you know what is a ring? Yeah, that's usual stuff. Only that here, normally while studying in physics, we assume that rings are commutative. In general, reality is harder than what we have during our studies, and rings used to be anti-commutative. So this is closer to that what physicists, mathematicians do. And a super ring is a ring where the ring has the composition as 0 with R1, like here. Okay. This is, and well, this is considered superspace. And the thing is that since this is a ring, the multiplication, the algebra structure is such that every element with this non-zero has an inverse. This is usual stuff. And when you have this thing, the only thing you have to take into account is, again, that the multiplication of homogeneous elements is compatible with the parity. The ring is supercommutative. If what you have is that, as before, again, this was with here, this way. Well, the super rings is exactly the same as before, but the difference is that the ring, the elements will be homogeneous. Well, as I said, they will be the elements will be an inverse. So now, a super ring is co-local if there is a unique maximal homogeneous ideal in such a way that this ideal, the intersection with here 0 with here 1 is such that you will have that this ideal is the composition I0, I1. And the following thing, there are modules and things and derivations of modules, and this will be also things that will go already to structures like vector fields, super vector fields, and things that will appear in supergeometry. So I think that it is a good place to finish. So thank you very much for your attention. I hope that this will be interesting to you. Thank you.
Thank you, Javi, for your talk, for your super talk, actually. Are there any questions or comments? Oh, what's this? Okay, now we see you. Are there any questions or comments?
Super comments?
Yeah, any super comment, Bartos, William?
I hope that someone understood something. The last time I saw this, it was pretty much difficult. So I guess that it was a little bit better.
I know, more or less we followed your talk. Very algebraic, actually, but very interesting. Super interesting, I would say.
I mean, the funny thing about it is that when you had differential functions in physics, they used to be Lagrangians.
Mm-hmm.
So the new functions in supergeometry are the differential functions and things of the sort. And what you do is just to do differential geometry considering these forms, okay? So you can do super contact, you can do super symplectic geometry, you could start super everything, Hamilton-Jacobi for super manifolds, everything. It can be done. K-contact, super K-contact, Darboux theorem.
Super many things.
You can extrapolate everything. Many things are done, but many things are left to do.
Okay, looks interesting. A lot of work to do.
Yeah.
So,
Well, many is done.
Yeah, many is done. Yeah.
But for example, as far as I know, there is no super contact.
Yeah, nor super BK symplectic. So
No, there is no super BK symplectic. Or there is no super, as far as I know, there is no super Hamilton-Jacobi equations or super stability.
Julia, did you hear that? There's no super.
Or super, or maybe I haven't never seen a super multisymplectic, for example.
Whoa, please.
Then these functions, super functions, they have exotic names in string theory and things like that. They love it.
Wow.
And they used to do things of the sort. So anyhow, that's all on my side.
So are there any more questions, comments, super comments? No? Okay, so I suppose we can stop now. And thank you, Javi, for your talk. And we'll see the second part next week. So see you all next Thursday. And goodbye.
Bye.